Vector space is one of the fundamental concepts in linear algebra that provide a mathematical framework for studying vectors and their relationship. It allows us to understand how vectors can be added together and multiplied by scalar while satisfying specific mathematical rules. The concept of vector space is widely applied in engineering, computer science, data analysis, artificial intelligence, and many other scientific fields. In this presentation, we will explore the essential topic of vector space, including subspace, spanning set, basis, row space, column space, null space, rank, and nullity, and understand how these concepts are connected in solving systems of linear equations and analyzing matrices.
The purpose of this study is to develop a clear understanding of the fundamental concept of vector space and their importance in linear algebra. This presentation aims to explain the properties of subspace, how spanning set generate vector space, and how a basis provides the minimum set of vectors required to represent every vector in a space. Furthermore, it introduced the concept of row space, column space, null space, rank, and nullity, highlighting their role in metric analysis and solving linear systems. By the end of this presentation, the audience should understand how these concepts are interconnected and why they are essential in mathematics and a real-world application. Before we dive into confusing formulas, how can we understand what a subspace means in the easiest way possible? Imagine a huge vector space is a large house. Inside this house, there is a small bedroom. This bedroom is what we call a subspace. Why? Because even though the bedroom is just a small area, a subset is still located inside the same house and it still follows the rules of the house. It has the same roof, the same wall, and uses the exact same electricity supply. So, in mathematics, a subspace is a smaller set inside a larger vector space, where the smaller set is fully complete and still obeys all the original law of the larger space. Then, according to our textbook, the definition of a subspace is a subset W of a vector space V is a subspace of V if W is itself a vector space under the vector addition and scalar multiplication operation defined on V. However, keep in mind that not just any random room or small set qualifies as a subspace. According to our textbook, to prove that a subset is a subspace, it must really pass two golden conditions under the subspace theorem. The first condition, close under vector addition. This means if we take any two arbitrary vectors, let's call them as a vector x and y, inside our set, when we add them together in bracket x plus y, the result must still remain inside the exact same set. It cannot escape outside of our room. The second condition, close under scalar multiplication. This means if we take any single vector x from that set and multiply it by any number or scalar alpha, the result in bracket alpha x must also stay inside that very same set.
Question 1. Let P2 be the vector space of all polynomials of degree or less. Thus S form a subspace of P2 as in bracket A plus Bx plus Cx squared, any element of P2. A equal to 2B minus C plus 3. U equal to A1 plus B1x plus C1x squared. A1 equal to 2B1 minus C1 plus 3. V equal to A2 plus B2x plus C2x squared. A2 equal to 2B2 minus C2 plus 3. U plus V in bracket A1 plus A2 plus in bracket B1 plus B2x plus in bracket C1 plus C2x squared. A1 plus A2 equal to 2B minus C1 plus 3 plus in bracket 2b2 minus c2 plus 3 equal to in bracket b1 plus b2 minus in bracket c1 plus c2 plus 6. 6 not equal to 3. U plus v not any element S. S is not a subspace of P2. Ku any element of S. Ku is equal to K in bracket A1 plus B1 X plus CA1 X squared equal to KA1 plus KB1 X plus KC1 X squared. Ka equal to K in bracket 2B minus C1 plus 3 equal to 2 in bracket KB1 minus in bracket KC1 plus 3K. 3K is not equal to K. In bracket 4, K not equal to 1. Ku not any element of S. S is not a subspace of P2.
Assalamualaikum and good day everyone. My name is Amira Aisha and I will presenting chapter 4.4 which is spanning set from MAT263 linear algebra. In this presentation, I will explain what a spanning set is and the procedure used to determine whether a set spans a vector space, and finally I will demonstrate the procedure through an example. So what is a spanning set? Let's begin with the definition of a spanning set. A spanning set is a collection of vectors that can generate every vector in a vector space through linear combination. Before we continue, let's first understand what a linear combination is. A linear combination is formed by multiplying vectors by scalars and then adding the result together. It can be written as C1v1 plus C2v2 plus Cnvn, where C1, C2 and Cn are real numbers called scalars and v1, v2, vn are vectors. If every vector in a vector space can be written as a linear combination of the vectors in a given set, then that set is called a spanning set. In simple terms, a spanning set contains enough vectors to generate every vector in a vector space. Procedure to determine whether a set Next is procedure to determine whether a set spans a vector space. There are two main steps to determine whether a set spans a vector space. Step 1. Choose an arbitrary vector from the given vector space. The form of the arbitrary vector depends on the type of vector space. For example, if the vector space is Rn, the arbitrary vector is x1, x2 till xn. If the vector space is Pn, the arbitrary element is a0 plus a1x plus a2x squared and till anxn. If the vector space is mmxn, the arbitrary element is any m multiple n matrix. And then step 2. Determine whether the arbitrary vector can be written as a linear combination of the vectors in the set. S equal to vector of v1, v2 and vn. If the arbitrary vector can be expressed as a linear combination of the vectors in S, then S spans the vector space. However, if there is at least one vector that cannot be expressed as a linear combination of the vectors in S, then S does not span the vector space. Now that we understand the definition and the procedure, let's look at an example to see how we determine whether a set of vectors spans a vector space. Here is the example for S spans R3. The question shows that the set S, which consists of the vectors 1, 2, 3, 0, 1, 2, negative 2, 0, 1 spans R3. Following the steps given, first, we choose the arbitrary vector. Since the vector space is R3, let x, y, z be an arbitrary vector. Then, we express vector as a linear combination. Assume A times the vector 1, 2, 3 plus B times the vector 0, 1, 2 plus C times the vector negative 2, 0, 1 equals the vector x, y, z. After that, we form an augmented matrix. Then, apply the Gaussian elimination method. After we apply the Gaussian elimination method, from the result, we can notice that there is a pivot in every column of the coefficient matrix. This means the system has a unique solution for every arbitrary vectors x, y, z. Therefore, every vector in R3 can be expressed as a linear combination of the vectors in S. Hence, the S spans R3. Next is procedure to determine whether a set spans a vector space. There are two main steps to determine whether a set spans a vector space. Step 1. Choose an arbitrary vector from the given vector space. The form of the arbitrary vector depends on the type of vector space. For example, if the vector space is Rn, the arbitrary vector is x1, x2 till xn. If the vector space is Pn, the arbitrary element is a0 plus a1x plus a2x squared and till anxn. If the vector space is mmxn, the arbitrary element is any m multiple n matrix. And then step 2. Determine whether the arbitrary vector can be written as a linear combination of the vectors in the set. S equal to vector of v1, v2 and vn. If the arbitrary vector can be expressed as a linear combination of the vectors in S, then S spans the vector space. However, if there is at least one vector that cannot be expressed as a linear combination of the vectors in S, then S does not span the vector space. Now that we understand the definition and the procedure, let's look at an example to see how we determine whether a set of vectors spans a vector space.
Today, I will present our solution for determining whether the given set forms a basis. Before we start, let me briefly explain what a basis is. A basis is a set of vectors that satisfy two conditions. First, the vector must be linearly independent. Second, they must span the entire vector space. If both conditions are satisfied, then every vector in the space can be written uniquely as a linear combination of the basis vector. This is the question given. We are asked to determine whether the set, which consists of these three polynomials, form a basis. To answer this question, we need to prove that the set is linearly independent and that it spans. First, we check whether the set is linearly independent. We assume that the linear combination of the three polynomials is equal to the zero polynomial. Next, we collect the coefficient of the constant term. By comparing the coefficient on both sides, we obtain these three linear equations. This equation will then be written in metric form so that we can solve them using the Gauss elimination method. Now, we solve the coefficient matrix using Gauss elimination. First, we interchange rule 1 and rule 2 so that the first pivot becomes 1. This makes the elimination process easier. Next, we perform roll operation to eliminate the entries below the first pivot, creating zeros underneath it. Then, we continue using the second pivot to eliminate the remaining entries until the matrix is in row echelon form. Finally, we normalize the pivot values to obtain the final matrix. From the final matrix, we can see that every variable has a pivot. Therefore, the system has only the trivial solution. Hence, the set is linearly independent. Next, we verify that the set spans. We let be any polynomial and express it as a linear combination of the vector in set. Since the system has a unique solution, every polynomial can be represented by the vector in the set. Therefore, the set spans. Since the set is both linearly independent and spans, we conclude that the set is a basis for P2.
Hi, Assalamualaikum. My name is Nurdani Shaifa. Today we are going to dive into 5 fundamental and interconnected concepts in linear algebra, which is row space, column space, null space, rank, and nullity. When we look at the matrix, it's not just a grid of random numbers. It's actually defined subspace that control how vector and data behave. Inside any matrix E, we can identify 3 fundamental subspace, which is row space is the subspace spanned by the row vector. Column space is the subspace spanned by the column vector. And the null space is the set of all vector x that satisfy the homogeneous equation Ax equals to 0. Furthermore, The dimension of the row or column space is called the rank, while the dimension of the null space is called the nullity. Let's look at the example to see how this connects. The first step to finding all these spaces is to reduce our matrix A into its row echelon form REF using elementary row operation ERO. Our original matrix is A equals to 5, 8, 6, 2, 2, 5, 2, 0, 9. First, we want to create a leading one in the first row. We can achieve this by subtracting twice the second row from the first row, which is R1 minus 2R2 equals to R1. Our first row now become 1, 4, negative 4. Second, we eliminate the number below this leading one in the first column. We do this by applying R2 minus 2R1 equals to R2 and R3 minus 2R1 equals to R3. Third, we create the second leading one in row 2 by dividing the entire row by negative 6. Finally, we eliminate the value below in row 3 and normalize the final row. This leaves us with a clean row echelon form, REF. As we can see, this matrix contains 3 leading ones, which means it has full rank. Step 2. Finding row space, column space, and null space. Using the REF matrix, we can directly extract the basis for our vector space. Row space. The basis for the row space consists of the non-zero row of our REF matrix. Therefore, the basis for the row space is 1, 4, negative 4, 0, 1, negative 13 over 6, 0, 0, 1. Column space. To find the basis for the column space, we look at which column contains a pivot leading one in the REF matrix. Since all 3 columns contain a pivot, we must select the corresponding column from the original matrix A. Thus, the basis for the column space is 522, 820, 659. Null space. We find the null space by solving the homogeneous system AX equals to 0 because our REF has 3 pivots for a 3 by 3 matrix. There are 0 free variables. This means the only solution for x1, x2, and x3 is the trivial solution where all variables equals 0. Therefore, our null space only contains the 0 vector. Null space A equals to 0. Last step, step 3, rank, nullity, and conclusion. Finally, let's look at the dimension of these spaces. Rank A, the number of vectors in our column or row spaces basis, which is 3. Nullity A is the number of vectors in our null space basis, which is 0. Let's verify this using the rank nullity theorem, which is rank A plus nullity A equals to n total number of columns, which is 3 plus 0 is 3. Our calculation perfectly satisfies the theorem. This proves that matrix A is invertible and its columns are completely linearly independent.
First, for spanning set, when we reduce the augmented matrix, if it is consistent, then S span R. But if it is inconsistent, meaning we get a row of 0 equal to a value, then S does not span R. Second, for subspace, we check the closure properties. If the axiom hold, it is a subspace. If they fail, it is not a subspace. Third, for basis, we convert vector into matrix column and reduce to row echelon form. If every column has a pivot, it gives a unique solution, meaning it forms a basis. Finally, for rank and nullity, after reducing the homogeneous matrix, the number of pivots gives us the rank, and the number of free variables gives us the nullity. Vector space provides the foundation for understanding many important concepts in linear algebra. The study of subspace, spanning set, and base help us understand how vector space are formed and represented efficiently. Meanwhile, row space, column space, null space, rank, and nullity allow us to analyze matrices, determine the number of independent vectors, and solve system of linear equation effectively. Together, these concepts are essential tools in mathematics and have practical application in engineering, computer science, machine learning, data science, and many other fields. A strong understanding of vector space enables us to solve complex mathematical problems with greater confidence and accuracy.